Hello and welcome to the third class on thermodynamics. So far, we have discussed the first law in a very broad-based manner applicable to different types of processes like isothermal, adiabatic, isochoric, isobaric, cyclic, expansion in vacuum. Today, we shall be spending time on solving some typical problems. Therefore, I urge upon you to interact with me without considering any other thing that I am recording this for the public. Doesn't matter. Since you are here with me, that will be more lively. The class will be more lively if you interact with me. So let me share my screen without any delay. Uh, good evening, Samidha and Priyani.
Good evening, sir.
Am I audible?
Good morning, sir.
Am I
Yes,
audible?
Yes, sir.
Yes,
yes, sir.
it is. Priyani is wishing me good morning is justified. Uh, Let me welcome those who are watching in the YouTube live stream or otherwise that I am delivering this lecture from the soil of United States of America. Presently, I am in San Diego in the California state. Therefore, one of the students, Priyani, wished me good morning. Okay, because we will be winding up first law and its extensive application. First law mostly talks about the conservation of energy and, to be more precise, the internal energy. In the universe, which consists of the system and surrounding, the net internal energy remains constant. The net internal energy remains constant. Whether the energy transit, I repeat, energy transit occurs through heat or, I don't say heat energy, heat or work, it changes the internal energy. Surrounding gives, surrounding loses, system takes, system gains, system gives, system loses, surrounding gains, surrounding gains, surrounding increases. So all this play of change of internal energy, but if you take the sum total of system and system and surrounding, that means the universe, the internal energy remains constant. It is always conserved. And if it is an isolated system, then we are not connected with the surrounding at all. Then inside that isolated system, which is completely insulated, the internal energy is constant. And to be much more precise, for the internal combustion engine or can be applicable to any system, including our biological system, uh, that the sum total, let me revise what we have done so far. The change in internal energy is equal to the sum of two currencies of energy, two transit modes of energy, that is energy which is coming from heat and the energy which is coming from work. Both heat and work are responsible to change the internal energy. As you know, heat and work, they are not energy, they are the function, thermodynamic function, not the state. They are not state variables independently, usually, unless this for adiabatic, this for isochoric. But in general, Q and W, these are the energy transit modes. They are not themselves energy. They are thermodynamic functions, but not state. They are not variables. And the sum Q plus W is always a state variable or state function. Sum, as you know. I'm sure I can have a feel that what you are able to understand, what you are not. When I feel that a part of my statement that I am delivering is not comprehensible, then I will tell you that this portion I will clarify later. But otherwise, you have the liberty to ask me, to interrupt me and ask questions. Don't be shy or don't shy away from asking me questions. I'm putting the participant list in front of me to see the raising of your yellow hand in Zoom so that I might offer you to ask question. Today will be going to be very interesting because this will be a numerical session and we'll try to finish first law. Because as I have already told you, viewers from YouTube, that this session, the thermodynamic classes, they will not only be meant for chemistry but also for physics. Now, let me tell you, this is chemistry. If it is physics, the only difference you have is minus W. Because the sign conventions here in chemistry is positive, work is done on the system, and negative by the system. But here it is positive by the system and negative on the system. And can anyone tell me that work done in a one-step process under a constant pressure condition, irreversible work done, is in chemistry, we take minus P delta V. This is the constant pressure, external pressure, delta V. V final minus V initial. In physics, what they take? Can you tell me? Tell me what, because I will tell you, acquaint with you when you are handling a problem in physics. He will be doing only this change. Delta U, delta S, delta S. Entropy is a phenomenon in the second law. It is still more interesting. That will come in the second law, entropy. But enthalpy change and internal energy change will come here in first law. Now tell me what the physics convention will make for work, irreversible work done. Yes?
Sir, plus P delta V.
Yes, plus P delta V. Because their sign conventions are opposite. If it's expansion, this del V is positive, then work is positive. So therefore, the expansion work for them is positive. It's done, work done by the system. But if del V is negative, is a compression, final minus initial becomes negative. So work done becomes negative. So the work done on the system, which we say positive, they say negative. Doesn't matter. They have their logic, we have our logic. The only thing this you have to distinguish. And once we apply that to chemistry, we will continue to to adopt the chemical convention called the acquisitive convention, and you can yourself change it to physics convention. So del U is equal to Q minus P del V. This is our convention. Therefore, we uh, bring Q to this side, one side, and take P del V to the other side. And we know that when pressure remains constant, this is the external constant pressure, then QP is nothing but equal to del H. That is the definition of enthalpy change. If a process is carried out, I'm sorry, V, if a process is carried out under constant pressure condition, then change in enthalpy is not same as the change in internal energy. The PV energy comes into force. There is a change in volume if it is carried out under constant pressure condition. Then this change in volume, del V multiplied by P, that when added to the internal energy will become QP, that is enthalpy change. These things you know. But I want to ask you, anyone who is watching directly from the YouTube live streaming, and I'm happy to find that many guys are watching my videos later. Few guys are watching now uh, on the live streaming mode, and I'm sure if you share this video, I'm telling to others, those who are watching in the YouTube, to share the videos to your friends, you will find many more things which possibly you will not find in your texts or in any source, because I'll be putting my entire experience in explaining through different practical examples. Now, coming to isothermal, so when you draw a P versus V graph, it will be isothermal goes with reversible. These two terms go with each other. If you keep the temperature constant by using a device called thermostatic bath, which will maintain the temperature at the fixed value. So you are carrying out an expansion process. Let us focus on expansion process or compression process. So you are going from A to B. This is volume V2 and this is volume V1. And if it is expansion, then V1 is initial, V2 is final. And if it is compression, the other way, the opposite. So, but since the reversible process is done infinitesimally slowly, so you go this way and return this way. So there is no change of any thermodynamic variable or function or property, either of the system or the surrounding. Both will attain its initial value when you reverse. That means after expansion, if you compress, you will arrive at the same initial state without producing any change in the surrounding. Particularly, the entropy will not be produced, as you know, although we have not discussed in details about entropy. That will be the hero in second law. Now, what I was saying, for this, can anyone tell me how you correlate the first law for any isothermal reversible process? Yes. Pranam Sibdat Mahapatra. Are you class 11 or 12 or next student? Can you write down Sibdat?
So,
Yes.
uh, sir, in isothermal process, the temperature will be constant. So there will be no change in internal energy. Um, yes,
So
yes.
when we practically solve problem,
Okay.
what relationship we find?
The
Sir,
heat
work done is
content
equal to
Yes.
Q equal to minus W.
Or W is
yes,
equal to
sir.
minus Q. Same thing. Q is equal to minus W, but these guys, physics guys, will write Q is equal to W because they say Delhi is equal to, oh, please don't mind if I sometimes write E in place of U. Please don't mind. Since physics convention is equal to Q minus P del V. I mean P minus W, and W is equal to plus del V. It means Q minus, so Q is equal to del U plus W, and W is equal to P plus P del V. So since this is equal to 0, del U is equal to 0 in isothermal process, so Q is equal to W, they will say. Never mind. Once you understand, you can handle any problem in chemistry or physics. So that is what we find. Then tell me what will be the adiabatic process. Adiabat, this graph is called adiabat. This graph is called isotherm. Adiabatic process, the graph is isotherm. Tell me, I am showing the graph. Starting point is A, but if you come to the same volume, what will happen to the graph and where does the graph lie?
So below the isothermal curve.
Precisely, Omkar is correct, below the isothermal if it is expansion process. But it is the compression process, it will be opposite. I will discuss after some time. So it will acquire less pressure because coming to the same volume in isothermal, there is no change in temperature. It is maintained by a thermostat. But since adiabatic expansion has happened when inside an insulator, inside a isolated system or in an isolated container, I mean in an insulated container, so it will lose its internal energy and the temperature will be lowered. Lower the temperature, lower is the pressure. That is the Amundsen's law or Gay-Lussac's law. So, uh, so for that, tell me how the first law can be used. And for that, del H is also equal to 0, isothermal. Because this is a ornamental thing. In every process we find del H. Since P and V are both varying, so the product PV is a constant, that is Boyle's law. The derivative of that is 0. Constant, that the difference, the derivative will be 0. So del U is same as del H. We know. What about adiabatic? Yes, anyone, guys?
So there will be no heat exchange, so Q equal to 0. Therefore, internal energy will be equal to work done.
Change in internal energy will be equal to work done.
Work done.
Therefore, adiabatic work done is a state variable or state function, a state property. particularly when you carry out a process adiabatically, then change in internal energy, sorry, the work done is path independent. And in this case, del H is equal to, as we shall see later, this is N Cp delta T. Just hold on for a while. We will be knowing that later. This carries little meaning because del H only pertains to a change in energy at constant or heat absorbed or evolved at constant pressure brings about another kind of energy called enthalpy, which includes internal energy as well as PV energy. It doesn't matter. And that that the area bound by a P versus V graph that gives you the work done. So the work done during isothermal, this is adiabat, isothermal expansion is more than the adiabatic expansion for the same volume change. Obviously, the area bound by the adiabat is less than that of the isothermal. I am talking of expansion. Coming to the isochoric process, tell me if it will be carried out in isochoric, we can't coin the term expansion or compression because the volume is remaining constant. So W will be equal to 0, right? Then guys,
Yes,
tell me
sir.
what is the relationship?
The delta U is equal to
So,
Q.
Precisely. So in this condition, the heat absorbed or evolved is a thermodynamic property. So Q isochore is a state variable, particularly in the isochoric process. Then tell me, in this situation, what will happen to the, supposing I show same P versus V graph, where do you place the change?
The
so
parallel
there
to
will
Y
be
axis.
no,
Yes, this will be a vertical line parallel to the p-axis where there will be some change. Tell me what change will happen with the change in pressure?
The temperature.
temperature change.
Definitely the Hamilton's law, as I was mentioning in some connection. Yeah, I was telling about that, but here it will be also applicable that temperature will fall. But this is not a temperature graph, but you have to bear in mind that since pressure is decreasing, the temperature has to decrease. Conversely speaking, the decrease in pressure is due to decrease in temperature. Decrease in temperature is the cause and decrease in pressure is the effect. So we can have it. And then for isobaric, that is very, this is called an this is called, the graph is called an isochore, and this is an isobar. And this PV versus graph is a straight line parallel to the volume axis. So that the area bound by the graph will be a rectangle, and this area will be giving you P delta V, that is the work done under constant pressure condition, which is usually irreversible. Well, if I say irreversible, don't take it in chemical parlance. I've told you, irreversible word is used in a very confusing manner. And it is as a meaning for internal combustion engine expansion and compression. It has some meaning, and in chemical process, chemical change, it has got a different meaning, nothing to do with speed, how fast a reaction occurs. But here, any sudden process, any fast process is irreversible. And ironically, such process can be reversed, but it will leave some change elsewhere, maybe in the surrounding. We'll talk about that later, slowly and steadily. And in a cyclic process, and this is, everything will remain. Del U is equal to Q plus W, that is equal to Q minus P del V. Everything will remain, nothing will cancel. So this Q, in place of, then write down NR delta T, because pressure remains constant. If there is a volume change, that is definitely due to change in temperature. Or conversely, the volume change occurs due to change in temperature, and here the Charles law comes into force. Temperature increases as volume increases, temperature has to increase, or because temperature increases during the line AB, therefore volume is increasing because pressure is remaining constant. Charles law. This is purely Amundsen's law or the Gay-Lussac's law. And finally, in any cyclic process, whether it has only one step A to B, then B to A, or multiple steps, when you return back to the same state, you will find a similar situation like the isothermal process. Since you are returning to the same state, then del U is equal to 0, and therefore Q is equal to, or W is equal to, Q is equal to minus W, or W is equal to minus Q. And then you also know that when a gas is expanded to vacuum, then everything is 0. If it is isothermal, Q is equal to 0, del is equal to 0, work is equal to 0, everything 0. If it is adiabatic, that also it is equal to del E is equal to 0, Q is equal to 0. And as such, work is equal to 0 because P is equal to 0. Now, I will like you to solve a problem here and to show you how, this problem we will be solving first. Consider a reversible quasi-static expansion. You draw the diagram and write the data. I will give you the file, so nothing to worry. To save time, guys, those who are studying directly from the YouTube source, you also will find this file in the description box after the class is over. So you draw the graph and write the data, and you have to, with me, you have to solve the numerical. Try to grab one calculator, somewhere lying in your home. That will be required. Consider a reversible quasi-static. Quasi-static is same as quasi-dynamic, because if any reversible process occurs infinitesimally slowly, entering into equilibrium at each moment, so that the external pressure is equal to internal pressure. So pressure is a variable. That means reversible processes are quasi-static or quasi-dynamic, same thing. Expansion of an ideal gas between the two equilibrium states A and C, A to C, given in the figure. If 515 joule of heat is added, that means the system absorbs as it traverses the path ABC, A to B, B to C. How much heat is required for the transition along ADC? Assume that the initial pressure at A is this, P2 final pressure is reduced 1.05 into 10 to the 5 Pascal or Newton per meter square. Yes, Newton per meter square. V1 initial volume is 2.25 times 10 to the power negative 3 meter cube, and the final volume is 4.5 into 10 to the minus 3 meter cube. Now, here we will prove that the heat absorbed, that is the work done and work done. Let me tell you, heat absorbed and the work done, they are independent of path. Let us first take ABC path. Have you drawn the diagram, guys?
Yes, sir.
Yes, sir.
So let us first take ABC path. We are coming from A to C, not directly, but indirectly, going from A to B and then B to C. Then first let us say work done in AB path. WAB. Tell me how much. So AB is an isotherm or an isochore or what? AB.
Sir, isobaric.
Isobar.
So this graph is an isobar. So isobar is P is equal to minus P, because this is chemistry class. P external constant pressure into V2 minus V1. V final minus V initial. Tell me, quickly tell me, the pressure, initial pressure is 2.1. Minus will be there into V final minus 4.5 minus 2.25. What is the difference? Because 10 to
Sir,
the power minus 3 is common. So it is again 2.25
2.25.
into
Yes,
10
sir.
to the power minus 3. So that will be joule, because all are in SI unit. So the answer, the work done, will be definitely coming in joule. So can you find me what is the value? So this 2.1 into 2.25,
Sir,
take a calculator into 10 to the power 2. How much?
sir, minus 4.725.
Tako, you multiply with 100.
Sir,
Multiply with 100.
minus 472.5.
This much joule of work has been done. So what is Q then? How much of heat has been absorbed? Since work is done by the system, and therefore it is coming negative in chemistry classes. So Q has to be positive. Sign conventions of Q are same in physics and chemistry. So Q is how much? Tell me. If W is minus 472.5 joule, work is done by the system, then Q is how much? Okay, forget about it. We'll talk about Q later. I'll talk about Q later. It's a difficult question now. So let us find out the work done in AB. BC. Because you can't tell what is the Q, because Q involves both P del V term and del U term. So del U, we have not discussed about del U. So WBC, tell me, is it an isobar or isotherm?
Isocoric.
EC.
Sir, isochoric process.
This is an
Work.
isocore. So work done is how much?
0.
The 0.
Del V is 0 means work done is 0. So the total work done is how much? In ABC, root, the total work done is minus 472.5 joules. Okay. Now let us see what is the total work done in ADC path. It is 0 plus, I am just taking speed. This is isocore, your first cooling down. Here you are fast heating to a higher temperature. This was at a lower temperature, T1. This is at T2. And then you are cooling to T3. Here you are cooling down to, say, T3, some T4, and then you are heating to T3. Right? You are coming to the same C. You are here first cooling down by reducing the pressure, you are reducing the temperature. Or the vice versa is really true. And then heating to come to the same temperature because C is a single state. Now, what is the total work done? This plus this isobar. Only work done is in the isobaric process. This from D to C. How much? It is minus
Sir,
P.
two,
What is P2? Look to the question. P2
sir,
is
1.05
1.05
into 10 to the 5.
Pascal into the change in volume is same. Change in volume is same. V2 minus V1, that is 2.25 into 10 to the power 10 to the power
Minus
10 to the
3.
power minus 3. So tell me what is the answer here?
Sir, minus 236.25.
Right? Now, since A, since del U is constant in both the process, because the two states are fixed, A and B. So, since internal energy is a state function, state variable, their changes are not dependent on path. Del U will remain constant whether you come via ABC or come via ADC. So, del U ABC is equal to del U ADC. So, what is del U? Del U ABC is equal to, according to our, this is Q plus W. Q plus ABC. Now, ABC, the question has given that the heat absorbed is 515 joule is given. So 515 plus, because it is absorbed, and the work done in ABC is minus how much? 472 point how much? 5. And the change in internal energy in ADC is equal to, supposing this is QABC is given, this is QADC which is asked plus WADC, that is equal to QADC is unknown, and this is 236.25, and these two are equal because internal energy is a state variable. So if you equate 515 minus 472.5 is equal to QADC minus 236.25, how much you are getting? QADC is how much? Calculate and tell me. Guys who are watching.
Sir, sir, 278.75.
7.
Yes, sir, 75.
So obviously, if the if there is no change in internal energy, so whatever work done will be there. That will be used up in doing work. So here the area bound by the curve is this much, what we found out, minus 200 something. And here the area bound by the curve is from here down to the x-axis. So more heat is required for ABC and less heat is required for ADC. More work has been done in ABC, less work has been done in ADC, obviously. So which proves that it is the Q and W, they are path dependent. But Q plus W That is, daily is path independent. In both the processes, daily is same. Daily is same. There has been a daily, but it's same. If you add Q and W in ABC, you'll get the same result as you add. Just I want to know what is del U. You take any one step. 515 plus minus work done has been expansion work. It is minus 472.5. So what amount the internal energy has increased? It has already done so much of work. So what is the amount of internal energy change that has happened? Tell
Sir,
me.
42.5 joule.
42.5.
Same thing you will find in a BC. Same thing you will find in ADC. It is the work done, the heat absorbed that we found out is how much? The answer. The answer we
Sir,
found out is
278.75.
and the work done is how much? The work done is 236.
236.25.
So what is the answer now? Is it
Sir,
not the same?
42.5.
Same. So the heat done, heat absorbed, work done, they are path dependent. In this, it is 515 and it is work done is 472. And in this, the heat absorbed is 278, work done is 236. But the del U is same because the states are same. A and B are fixed states. So difference in any state variable will be independent of path. Interestingly, can you tell me from the data that AC is a thermo isotherm or an adiabat? Had the temperature data would have been given, then would have found out what would have been the work done through this. If it is an isotherm, then you can find out the work done by the equation that you remember, minus nRT, 2.303 nRT log V2 by V1 or P1 by P2. So, yes,
Sir,
any answer? Is it an
sir,
isotherm
no,
or
sir. Sir,
adiabatic?
sir, Adiabatic because del U is not zero here.
No, 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 no. Uh, del U is not zero here. Since del U, see, he's saying that since del U is not zero here, it is having 42.5 joule during AC. So it cannot be an isotherm. It has to be an adiabat. What do you think, others?
Yes, sir. The same.
Had it been an adiabat, then you would have found whatever work heat is absorbed is totally spent out in doing work. Absorbed means it is spent out doing work. Evolved means the surrounding will do work on the system. Okay, with this interesting discussion, we'll go to this problem. Quickly handle it and finish in 1 minute. A sample of an ideal gas is allowed to expand from an initial volume 2 liter to final volume 3.5 liter. Guys, need not have to write down this problem because you have to go a very long way. So have patience in you, and we are going to make our session more and more interesting as you enter into the heat capacities of gases, and also talk about the principle of equipartition of energy, giving you the degrees of freedom so that you can find the relationship between Cp and Cv with the gas constant, how they vary. So this will be more interesting. So let us finish this formality. Sample of an ideal gas is allowed to expand from initial volume 2 liter to final volume 3.5 liter as against a constant external pressure. P external is 0.995. At the same time, 117 joule is transferred from the surrounding to the gas. That means gas absorbs. So Q is equal to plus 117 joule. What is the total change in internal energy? This is first law. So tell me, U is equal to Q
So,
plus W. Q is
yes, sir.
117 and this is, and Q, W is our P del V. Minus will be there in chemistry. So P is
0.995.
so we'll be doing later. So first, let us find out W is minus P del V. P is 0.995 and 3.5 minus 2. So V2 minus V1 is 1.5, I guess. So this will be minus. So it will be minus how much?
Sir, minus 1.49 ATM liter, which is minus 151.19 joules.
Yes, precisely. We find the answer in atmosphere liter. This is atmosphere, this is liter. But we know the conversion value. 1 liter atmosphere is 101.3 joule. So we can multiply with 101.3 joule. So you get how much joule minus?
Sir, 151.19. Sir, yes, sir.
And then you have to add. So total change in internal energy is Q plus W. Q is 170, out of which it has lost, due to the expansion work, it has lost this amount of internal energy in the form of work, minus 151.19. So what is the answer?
Sir, minus 34.19.
That means there is a net decrease in internal energy. It has got 117, but lost more than what it got. So there has been a decrease in internal energy. So let's take the second one. A sample of an ideal gas in a cylinder of an engine is compressed from 400 ml to the initial is 400 ml. V final is 50 ml. There is a compression. During the compression, stroke against a constant pressure is 8 atmosphere. So a lot of work will be done because although we are going from here to here, not in a reversible path, but in this path we are going. So the work done will be definitely more in compression, as we know. So at the same time, 140 joules of energy transferred from the gas to the surrounding. That means the as heat. So Q is equal to minus 140 joule. It cannot take all the work. It's a very gentleman. The systems in the universe, when it is in contact with the surrounding, behave as gentlemen. Gentlemen. So it will not take all the work that has been done upon it due to compression to increase its internal energy. A part of it will be, given as return gift, as I used to call return gift. So what is the return gift? W is equal to minus P del V, and this is minus 8 atmosphere into V final minus V initial. Final is 50, initial is 400. So there will be negative, negative will be positive, but in physics it will be negative, but in chemistry it will be positive. Why these guys are not sitting together and make these conventions identical? I really feel very sad about it. There must be unanimity in the sign conventions. They are logical in their own way. We are logical in our own way. So how much?
Sir, 2800 joule.
2800 joule. Is it okay?
No, sir.
How?
So plus
Oh, sorry,
Sir,
plus. Plus
sir,
how much?
283.64 joule. So it is in ml.
No, first we have to make it a liter. Yes.
Yes, sir. Yes, sir.
Then this will be 0.05 liter minus 0.4 liter, right? 0.4.
Yes, sir.
So this is coming how much liter atmosphere? Plus because this is
Sir,
atmosphere, this
2.8. Sir, 2.85.
2.85 liter atmosphere. So to convert it
Sir,
to joule,
sir, only 2.8, sir. Sorry, sir.
only 2.8. Okay, no problem. So into 101.3, so how much it is coming? Plus
283.64.
so did you understand, Priyani? The mistake?
Yes, sir.
And now we have to add up. The net change in internal energy is Q plus W. Q is minus 140 because it is gone out of the system in the form of heat. The energy has come in the form of work and the energy has gone in the form of heat. Doesn't matter. And this is plus 283.64. Then what is the net change?
Sir,
143.64.
143.64.
1
43.64.
I think this answer is wrong. I'll check. 400 to 50. So 0.05 minus 4 and 8 atmosphere is the constant pressure. So if this is the case, plus and 140 is the energy that is dissipated out in the form of heat, then this is the wrong thing. I will check. It will be plus. There will be increase in internal energy by 143. It actually 143 होगा था 283 8 आएगा. So I have copied by haste. Which one? The work done, but not the change in internal energy. So this is wrong. Correct answer is 143.6. Okay, look to the second one. We have so many problems. These are simple ones. And we will find how interesting the problems will become as time proceeds. If heat evolves, this is a chemical process. Remember, in our class, we will be dealing with all types of processes. Physical processes like expansion and compression, where the reversibility, irreversibility have different meaning. And in chemical systems also we'll be dealing reversibility, irreversibility have different meanings. And also we'll be taking up physical change, melting, boiling, transition occurring between two allotropes. These are physical changes. But expansion and compression, they are not changes. These are processes. They are not processes. They are not changes. It is in the gaseous state. It also remains in the gaseous state. So, if the heat evolved for the following reaction at constant pressure, del H, which is equal to Qp at 25 degrees Celsius is minus 320 kilojoules per mole, then find the heat evolved at constant volume. What is del U, which is equal to Qv. So you have to use this. Who can tell me? Del H is equal to del U
plus delta nRT.
Yes. P del V will be replaced by del nRT in chemical change. Temperature remains constant. Same temperature. Here, the difference between Qp and Qv is due to change in the number of moles. If there is no change in number of moles, no change in volume, then Qp same as Qv. Better call it Qv. Why to defame Qp? So let us find out. So this, what is del n here? Can you tell me what is del n here?
Sir,
So
minus
minus
0.5.
This will be
minus 5.
cancelled. This will be cancelled. Solids and liquids are not considered. Only gas. 7 minus 15 by 2. So minus
0.5.
minus 0.5. So let us find out what is del U, which implies del U, which is being asked, is del H minus del nRT. So del H is minus 320 kilojoules or in kilojoules, and del N is minus 0.5. Minus, again minus 0.5. No, yes, minus 0.5. R is as 8.3 because we are not 8.3. It is 0.0083, right? Because we are
Yes,
dealing
sir.
with kilojoules, we have to make 8.3 as 0.0083 to make it kilojoules into temperature. Temperature is 298 Kelvin because 25 degrees Celsius is 298 Kelvin. So here we can find out. Numerically it will be less. Can you find out quickly?
Sir, 318.78.
Plus or minus?
Sir, minus.
So we must say that. 318.78
78.
kilojoules per mole. That means, had this reaction been done in a constant volume condition, in a sealed container without any room for keeping the pressure constant, the pressure would have been reduced because there has been a decrease in the number of moles, and that condition, the heat release would have been 318.78 rather than 320. So that is the change in real internal energy. P del V is the work done. It has been gifted away, return gifted away. Now come to the next one. So next time when you are hosting someone, be prepared. They will be bringing some gift. You be prepared with some return gift. That has been the norm thermodynamics has taught us. Okay, 1 mole of an ideal gas undergoes a change of state from 2 liter 3 atmosphere to 2 atmosphere 3 liter. That means pressure remaining constant. So it is a isobaric expansion 3 to 7 with a change in internal energy. Del U is 30 liter atmosphere. Calculate the change in enthalpy. This is same. Del H is equal to del U. Since it is a physical process, expansion process, del U plus P del V. So Del U is how much?
30 liter atm.
30 liter atmosphere plus P is 2 and del V is 7 minus 3. So it is 4. So 30 plus 4 to the 8 is 38 liter atmosphere. So the answer is given in liter atmosphere. So you can also change it to joule, doesn't matter. I'm sure you can understand this. We have already discussed how, the Q independently, Q and W, they are path dependent. In this, it is taking more heat, more work. In this, less heat, less work, but the change is same. Because change, I mean, the sum of these two. I am saying change because W is negative, because the sum is same. I mean, the heat plus W, which is del E, is same. See, now comes a new thing. You have to write down a little bit things. Heat capacities of gases, there are two types. Unlike liquids and solids, unlike liquids and solids, which have got only one heat capacity. And when I say heat capacity, it is an extrinsic property. It depends on the entire bulk, whether 1 mole, 2 mole, 5 mole, 7 mole, whatever. So it is an extensive or extrinsic property. And that is the amount of heat absorbed to raise the temperature by 1 degree Celsius. And mathematically, there are, I mean, in gases, there are two heat capacities. In solids and liquids, only one, and that is called heat capacity at constant pressure, constant 1 atmospheric pressure onto their heads. But gas is a gas. It's an enclosed container, there is a gas. It may not be in sync with 1 atmosphere. If there is a movable piston, then, and you are leaving it in the care of atmosphere, then the pressure inside and outside remains the same. But you can have a closed system. You can have a completely sealed system where more pressure can be built up, where you can use the Hamilton's law, increase the temperature, increase the pressure. So, or you can use a thermostatic bath to maintain constant temperature so that P and V vary inversely in a very systematic basis, the curve, Boyle's law curve, or sometimes adiabat running below for expansion. Let me tell you. We'll see what will happen, compression, adiabatic compression, that will run above, just the opposite. See that. Now, mathematically, again, I'm saying mathematically, if you have a gas and make a sealed container, don't allow the volume to change, and you see how much of heat it is absorbing for 1 degree Celsius rise. It will be definitely less than if you live into the care of atmosphere. That means make the pressure constant and do the same thing. See how much of heat it is absorbing for raising 1 degree Celsius or 1 Kelvin. You will find that heat is more. So there are two heat capacities values. One is called Cp prime. Prime I am writing here only to distinguish between molar heat capacity, which is primeless, simply Cp in my abbreviation, and Cv without prime will be molar heat capacity at constant volume, and this is at constant pressure. So mathematically, it is the small little heat that is absorbed and small change in temperature at constant volume, or because QV is equal to del E, So del E by del T at constant volume, and Cp dash is equal to del H by del T, because Qp is nothing but equal to del H, change in enthalpy, by change in temperature, not T, change in temperature. When we study entropy later in our next class, you'll find this will be the constant T. Here this will be differentiation, the slope of the line, but there the integration, the area bound by the curve, that is completely different. We'll talk about that later. Same thing, only delta T will be only T, and this delta T will be only T, then that will be the entropy change. We'll talk about that later. Don't worry. So have you written down these two lines? These two lines.
Yes, sir.
Yes, sir.
And this line also, right?
Yes, sir.
You make a change here, Cp prime and Cb prime and Cp prime here. Now you see the graph. These are the twin graphs, not twin, triplet graphs. The x-axis is temperature and y-axis can be internal energy. The red line is internal energy, U, and the blue line is H. And this we will be studying later, entropy line. Forget about entropy. Absolute entropy. That will be known from the third law. But entropy is introduced in the second law. Now, enthalpy, you know, numerically is always greater at every temperature. Enthalpy is greater. As the temperature increases, the internal energy increases as well as enthalpy increases. If it is a gaseous system, the PV energy also increases. So the enthalpy line lies above the internal energy line, and the slope of the line is nothing but Cp and Cv. The slope of this line at any point, this is really a curve, it's a mild curve, but we take it as a straight line for a small narrow range in temperature. We take it as a straight line, and the slope of the line is dE by dE by dt, or qV by dt, dE by dt, that is Cv, and the slope of this line is dH by dt, that is equal to Cp. I hope you understand. Do you?
Yes, sir.
Hello
Yes, sir.
guys. Hello guys who are watching from YouTube. Can you have a word with me in chat box? Is it going fine? Okay. Now, we are now in this phase, gas. It is a straight line. But if we consider from the solid to liquid, then gas, then if I during phase transition, the the graph will have inflection. So the Cp will change, and these are all Cp's up to this will change enthalpy. But here, when you come to gas, there will be two lines. If this will be for whatever is given is for H, let us extrapolate this line for H, and there will be another line going below it is for E, and this is for H. And it will be almost a straight line. The slope of the line will give you Cb, and slope of this line, which is slightly greater, dH by dt, give you Cp. Got it?
Yes, sir.
So you write down
Yes,
this write down, if you take a large change, instead of a small change, small delta, take a big delta. So Cv prime is equal to delta E by delta T. So del E or U, make it U. I'm just copy pasting. It was there long since, so I'm trying to change it. So del U is equal to Cv prime del T. But if we talk to molar volume, molar heat capacity, you multiply by the number of moles. Now, This is the equation that we'll be using to solve problems. The change in internal energy that is at constant, that is the heat absorbed or evolved at constant volume is N number of moles into the molar heat capacity. I have written below what is Cp and Cv. They are the molar heat capacities at constant volume and constant pressure respectively. Just write down this. Similarly, Cp prime, which is the heat capacity, which is an extensive property, but molar heat capacities are intensive property because you have specified 1 mole. So Cp prime is del H by del T. So del H, change in enthalpy or heat absorbed or evolved at constant pressure, is Cp prime into delta T. In place of Cp prime, we write N into Cp. So this will be our equation. Wherever there will be delta T, you can find out delta H from this simple relationship N into Cp delta T. Over. And also write down N is the number of moles.
Sir.
Write down N is the number of moles. Samita, are you there?
Yes, sir.
Priyani?
Yes, sir.
Okay. And the interesting relationship between molar heat capacity at constant pressure and molar heat capacity at constant volume is that difference is always a constant, gas constant R. On a later occasion, not today, I will make a proof how we get Cp minus Cv is equal to R. Maybe today, as per my planning, I don't know how far I can proceed. Let's see. And for monoatomic gas like helium, krypton, xenon, Cv is approximately equal to 3 by 2 R. And Cp is 1 R plus. You add 1 R, you can get that is 5 by 2 R. In diatomic gas like O2 and 2, at moderate temperature condition is 25 to 70 like that. Cv is equal to 5 by 2 R. Cp is equal to 1 R more, 7 by 2 R. In polyatomic gas like ozone, like N2O, like SO2 polyatomic gas, more than two atoms. Then it is Cv is equal to 3R and Cp is equal to 4R. Why this is the case, I will tell you in a nutshell. Bringing in the principle of equipartition of energy, I'll give you an idea about the degrees of freedom. So then only you can have a clear idea why this relationship is a valid 3 by 2 R for monoatomic, 5 by 2 R. I'm talking of Cv. Cp is undoubtedly 1 R more, and for polyatomic 3R. And the ratio of Cp and Cv, that ratio is called the Poisson's ratio, not the poison which when taken will create health issues, maybe death. Not that. Poisson, it's the name of a person. Poisson's ratio. Cp by Cv for monoatomic, if you just take the ratio 3 by 2 by 5 by 2, 5 by 2 by 3 by 2, so it is maximum for monoatomic, 1.67. You just write down this. Please write down.
Yes, sir.
So to keep you busy, I will be talking, always talking and talking. But you write down. To save time, I have put it here. And the Poisson's ratio, which is represented by gamma, is maximum for monoatomic 1.67 and 1.44 diatomic, and minimum for polyatomic 1.33. Now, this, you just listen to me. You write down, because the file I will give it to you. So you will write later. Why? Because monoatomic gases, when argon is there, helium is there, it has only translation. It doesn't have rotation. When it is an axis, there is a bond, and at least a diatomic, unless it is minimum diatomic, it cannot rotate about its axis or any axis. So only it will have a translatory motion. And in fact, the translatory motion can be resolved into three components, into x coordinate, y coordinate, and z coordinate. So the different coordinates in which the energy is stored, the internal energy is stored, they are called the degrees of freedom. Don't take it in a literary sense. Independent, freedom, no. Degrees of freedom are the different modes of energy storage, internal energy storage. So for monoatomic gas, there is only translation, and the translation is expressed by three coordinates, x and y and z. So 3. For all molecules, there is only 3 translatory mode of degrees of freedom. So the energy is stored in x, y, and z coordinates. So that has been the norm in thermodynamics. So, and the principle of equipartition of energy says, yeah, this is the interesting thing, that every degree of freedom will take away the same energy value for storage. That is half nRT for n moles, half kT, half kT for one molecule. K is the Boltzmann's constant. Half RT for one mole, and half nRT for n moles. That is the energy stored for each degree of freedom. So if there are 3 degrees of freedom, and 3 into half nRT, so 3 by 2 nRT will be the absolute internal energy. But if there is a change of internal energy, there will be change in temperature, because N and R are constant. So del U is equal to 3 by 2 nR delta T. So if you correlate between del U is equal to N CV delta T, you will find CV is nothing but equal to 3 by 2 into R. So I have written that. There is no need of writing again, since CV, this if I write down, previously we got del U is equal to N CV into delta T, and if you compare, yes, written here, I'm sorry. If you compare between these two, then you will find CV is equal to 3 by 2 R, which we have written here without any proof. But here, this is the proof. Why? For monoatomic gases, the CV is equal to 3 by 2 R, and Cp will be 1 R extra. Cp minus Cv is always equal to R, or Cp is equal to Cv plus R. Now, if it is a diatomic gas, it has, at moderate temperature, 2 rotational degrees of freedom are added up. Pre-translational is common for all molecules, whether it is monoatomic, diatomic, or polyatomic. But in addition to that, 2 rotational degrees of freedom, because the diatomic molecule has a bond, and it will rotate. The rotation about the molecular axis is no rotation. This is not considered as rotation. But the rotation about the other 2 perpendicular axes, supposing the molecular axis is x-axis, the rotation about y-axis and rotation about z-axis, that there will be 2 degrees of freedom for rotation, rotational degrees of freedom. This molecule is the molecular axis, then it is rotating along this axis, this, and rotating about this axis. So only 2 degrees of freedom for rotation are accepted for a diatomic molecule. So 3 plus 2, 5. And as you know, for each degree of freedom, the share is half nRT and there are 5. So 5 by 2 nRT. You compare between del U is equal to n CV delta T. So CV becomes equal to CV equal to 5 by 2R usually for diatomics. But here is a caveat. That is a caution that I am making, that unless the temperature is high, vibrational degrees of freedoms do not come into force because the energy gap is so high. In ordinary temperature, even 100 degree up to 100 degree, the molecules will not be elevated to the excited vibrational level. Therefore, vibrational degrees of freedom will come in only at very, very high temperature, say 500, 300, 400, 500 degrees Celsius. Then only you have to add uh, two more. Why two more? Because in all, in a diatomic molecule, there are 3n minus 5 degrees of vibrational freedom. Vibrational degrees of freedom, where n is the number of atoms and 3n minus 5 is the total number of vibrational degrees of freedom. If it is a diatomic molecule, n is equal to 2, then 1. But remember, in vibrational mode, there will be always a pair, that as you have studied in force, force always goes in pair, action, reaction. Similarly, in vibration, it goes by a pair, both potential, vibrational degrees of freedom and kinetic. Once a bond is vibrating, just like a spring, as a bond oscillator, is a simple harmonic oscillation, there is always a kinetic energy and potential energy. So when you get one, means two, one kinetic, one potential. If you will get, supposing for polyatomic molecule, the rule is 3n minus 6, total number of vibration degrees of freedom. But that is the total number into 2. We have to multiply by 2 for potential and kinetic. So supposing ozone, which is a nonlinear molecule, n is equal to 3, 3 3s are 9, minus 6, 3. So 3 vibrational modes, but the total number of vibrational degrees of freedom will be 3 into 2, 6. Right? Each vibrational mode goes as a pair. But let me give you this caution that at moderate temperature, vibrational degrees of freedom are not considered unless it is high temperature. So if it is high temperature, additional 2 has to be added, 2 for diatomics, 2. So 7 by 2, which we take for polyatomic, can also be taken for not 7 by 2. 7 by 2 is the CP for diatomic. I'm sorry. 7 by, no, nothing. 7 by 2 is nothing. So you can take 7 by 2 if required, if you are given that it is a very high temperature. So you must know, must have this idea that at low temperature, even this rotational mode, they also do not come into force. Rotational degrees of freedom is invalid, doesn't carry any energy at low temperature, 0 and all that. So 3 by 2 also goes. But at ordinary condition, moderate temperature, say 25, 30, so rotation comes into force. So 3 plus 2, 5. So 5 by 2R is CV for diatomics. But it can be 7 by 2 if you are carrying out a process at very high temperature. So usually it is 5 by 2. It can be 7 by 2. It can be also 3 by 2 at very low temperature. But polyatomics, instead of having 3 translational degrees of freedom, there will be 3 rotational degrees of freedom. Now for diatomics, the rotation about the molecular axis is not considered as rotation. It carries no energy. But in in nonlinear polyatomic molecule, all the three axes, rotation about all the three axes will reserve one degree of freedom each. So there will be 3 degrees of freedom for polyatomics. Plus this 3n minus 6 into 2 that I have written, that I have cancelled, because at ordinary conditions, temperature conditions, the vibrational degrees of freedom do not come into force. So 3 plus 3 is 6 are taken for polyatomics. Vibrational degrees of freedom are not active at moderate temperature. So 6 into half nRT, that gives you 3 nR delta T. Del U is equal to 3 nR delta T. Therefore, Cv is equal to 3R, and hence Cp is equal to 4R. So these derivations on the basis of the principle of equipartition of energy, you don't write now in your copies, but you definitely write later. You can leave some space and write later, right? I think you understand. Raise your hands who have understood. I swept this discussion in haste. So, because that is not of much importance to you, because I know guys like, Rudra and maybe Omkar and others might be interested to know everything in details. So I thought of not telling you in details, but in non-detail, and I'm sure you have understood. Coming to most interesting part, let me see how far we have gone. Yes, I think it may be more than 2 hours, but we will be finishing. What do you say, guys?
Yes, sir.
Yes, sir.
Uh, so, guys who are watching from the YouTube, have to keep patience, because you are at home at liberty, you are not interacting with me, but you have to be definitely glued. You have to be glued with me with your pen and paper, and on the screen sometimes you have to pause the screen and write. That liberty you have if you are watching seriously in YouTube. You can pause as many times as possible. Now see, we are now coming to an adiabatic process, where expansion, we will be talking first about expansion and compression. Although I have told that even in non-adiabatic process having a dithermic wall, if anything is done very fast, irreversibly, then it will be treated as temporary adiabatic process. There will be, decrease in temperature as you suddenly expand, even if there is an adiabatic, a dithermic wall, but within no time, with small time, there will be thermal equilibrium. But in adiabatic process, there will be no thermal equilibrium with the surrounding. Equilibrium will be built up inside the isolated system, that will be happening totally isolated from the rest of the universe. That is what we call the surroundings. Now, for both reversible, just like in any other process, you have fast and slow, infinitesimally slow process. In adiabatic also, you have irreversible expansion, irreversible compression, or reversible expansion and reversible compression. For both irreversible and reversible process, maybe compression or expansion. So the adiabatic work done, since Q is equal to 0, goes without saying, the adiabatic work done is change in internal energy, which is equal to, now we know it is equal to mCv delta T. It is both. But delta T, they are not same for both reversible and irreversible process. Delta T in expansion is large in reversible than irreversible. There is a cooling effect, as you know, expansion is associated with cooling because there is a decrease in internal energy. I think wrongly said Hamilton's law. No, the decrease in internal energy, I mean, is the cause of decrease in temperature. It is nothing to do with the Hamilton's law. I withdraw the statement. I said yes, in isochoric system, it is the Hamilton's law, but in adiabat, the decrease in temperature happens because you spend your own energy. The system spends its own internal energy. So the temperature falls down. Because these things are so very interesting. And to, I can take hours together to talk about thermodynamics. But therefore, in order to avoid my temptation to go wild, I have prepared this lecture so that I will at least restricting to those which have been laid out for today's lecture. Maybe it is a 2.5 hours lecture. Now, if you carry out the adiabatic expansion, maybe the graph lies below the isotherm, but it is a curve. But adiabatic irreversible expansion again is the small little rectangle below, because it is again done under constant external pressure, which is the final pressure with which it will be given. Suddenly, the high pressure will be replaced by the low pressure. So always the work done in reversible expansion, whether it is isothermal or adiabatic, is more than the irreversible expansion. So, but this is applicable for both, because delta T is not same. The cooling effect is more profound in reversible because the work done is more, the area bound by the adiabat is more than the area bound by the small rectangle. So the temperature decrease, the fall of temperature is more. Supposing we started with 300 Kelvin, in reversible adiabatic expansion, we drop down to 200, but in irreversible expansion, we drop down to 220 or 230, which is greater than the reversible expansion. But in both the cases, there will be cooling effect because the internal energy has been used up performing the work, right? The above equation, but for only irreversible, for please give me 1 minute time. Just in the meantime, you relax. You can answer the call of the first nature. If it is second nature, well, yes, it's not good to, not answer the second nature. I give you 1 minute, maybe really 2 minutes time. And so guys who are watching from remote places can, I mean, remotely, that means they also can take 2 minutes break. Don't go away anywhere. Be in the vicinity of your number 1, number 2 center and come back immediately. And if you are hungry, then ask your mom or dad. In some cases, dads are more active than moms in this context, taking care of children's education. Ask them to provide some snacks. I think in India, you must not have taken dinner. Unlike here in Western countries, we take dinner at 7, max 7. And in India, when I was also in India, I never have taken my dinner before 9. Because once we take dinner, we fill our stomach, then an irresistible drowsiness will cripple us and we can't do anything. Sleep. I don't know how you guys are so night guys. You remain awake throughout night or maybe late night. I don't know how. Fill the stomach, you must be feeling drowsy. How you overcome this drowsiness? Okay, bye. See you soon. Now I'm back. I'm back. With a little bit of energy, internal energy. I will tell you in some other day. The funny part of first law, how it is applicable to our biological, our metabolic processes. Okay. So for only irreversible process, this is applicable. This one, I'm sorry, this one. This is applicable for both reversible and irreversible. But this is applicable, that is similar to the non-adiabatic process, the external constant pressure into del V minus sign is our prerogative, chemistry prerogative. So the same principle will be applicable for adiabatic. So if you equate these two equations for irreversible and CVDT applicable for both, that means for irreversible, and this only for irreversible. So from this, we can find out the actual temperature. The initial temperature is given, delta V is known, and the final temperature that it will attain, you will find which will be more than what it would attain by a reversible expansion. I'm talking of expansion. In reverse, have you written down all this?
Yes, sir.
Yes, sir.
Yes, sir.
In adiabatic expansion or compression, adiabatic gas laws will hold good. Just like in non-adiabatic processes, PV is equal to constant, because here PV will not be equal to constant, because with the change in volume, change in temperature is also happening. So here the rules are different. These are called adiabatic gas laws, where the counterpart of temperature, volume, here everything changes. Expansion, the volume changes, temperature drops down, and also pressure often is reduced. So here T V into gamma minus 1 is constant. That is T1 V1 gamma minus 1 is equal to T2 V2 gamma minus 1. Other adiabatic gas laws, like the Boyle's law, PV to the power gamma is equal to constant. P1 V1 gamma is equal to P2 V2 to the power gamma. And temperature pressure correlation is nothing is constant. So T1 by T2 to the power Cp is equal to P1 by P2 to the power R. You write down these three because we'll be solving problems. Very soon we'll be solving problems. For adiabatic expansion or compression, we have to use these laws as it is required. Mostly it will be required this. First one will be required. Volume, initial and final volumes are given. The initial temperature is given. You will find the final temperature. You will find this temperature will be lower than the lower temperature that you found for irreversible expansion, which expends lesser amount of work than reversible expansion, which is the area bound by a curve. Maybe that area is little less than had it been isothermal expansion. Over. Have you written? Those who are watching
Yes,
TV,
sir.
don't simply watch, but
Yes.
study with me. You will find interesting problems will come, and you will solve it with no difficulty. Now see, in adiabatic expansion, the final temperature in reversible process is lower than irreversible process, as more work is expended in the former. Adiabatic irreversible compression, on the other hand, results greater temperature. The work done is a big rectangle. Is the big rectangle which is more than the reversible compression. Adiabatic. So the final temperature in irreversible compression is more than the final temperature in reversible compression. Although in both the cases temperature will rise, just like in expansion, in both the cases temperature will fall. In the compression, the final temperature in a reversible process is more than that in a reversible process. Could you write down that? And also interestingly, for every state, initial or final, Pb is equal to nRT will be holding good. There is no gamma here because that is during the curve P, that is the adiabat. Pb gamma is equal to constant. T1 V1 gamma minus 1 is equal to T2 V2 gamma minus 1. That is variation. But once it comes to equilibrium, initial, final, then Pb is equal to nRT applicable for both initial and final states. You just write down this and then we'll be entering into problem session. Please bear with me. I'm doing some uncivilized thing. Taking a cup of tea with some snacks. Please. Himanshu Manjari Patra. She writes, she is in fit. She is now fit in Guwahati. I was qualified uranium exam in 2020 in 9th class. Happy to know that you are quite settled in Guwahati. Must be doing your IIT in Guwahati or something like that. Or IIT Guwahati, yes, you have written IIT Guwahati, yes. You please also watch Himanshu Manjari, how we are proceeding in our thermodynamics program. Just you must be a second year student in IIT Guwahati. Written? Writing is over?
Yes, sir.
Yes, sir.
Okay. Now, before entering into problems on adiabatic expansion or compression, let us take up the isothermal and reversible goes side by side. Buy one, get one free. Isothermal process can never be fast. They have to be slow and reversible. Okay. Let us grab our calculators. 10 gram of argon was compressed isothermally and irreversibly. So what is the work done? Work done is equal to minus 2.303 nRT. Since volume data is given, log V2 final volume by initial volume. When I write V2, I mean final. V1 means initial. So find out. 10 gram is 10 by 40 moles. 40 is its atomic mass because it is a monoatomic gas. R is 8.3. Answer will be coming in joule, and temperature is 300 into log V final. V final is 5 by 10. So it is minus log 2 minus will be plus, and this will be 2.303. This is 0.25 into 8.3 into 300 into 0.301. I have made it minus log 2 minus plus. So what is the value, final value? Grab.
Sir, 431.5.
If this is W, which is definitely compression work in our chemical convention is positive, so this is plus, then obviously Q is minus. The heat is evolved, and that evolved heat has been entirely used in performing work on the system. There is no change in internal energy. So Q is minus 431.5 joules. And since it is isothermal, del E and del H both equal to 0, that we know. Then coming to the second one, which is an insulated container. The moment you find insulated container, you are sure about adiabatic process. 1 mole of an ideal gas is subjected to a reversible expansion from 600 to 300. Had it been irreversible, then it would have been more than 300, maybe 350. We shall be doing that, because the extent to which we shall discuss will be needed for advanced level, IIT advanced level, and physics also advanced level, not the board level, or maybe some of the questions are coming in IIT mains. Very typical graph based questions are coming. So look to that also. Calculate the work done in monoatomic gas, diatomic gas, and also calculate Q, W, delta E, del H for monoatomic gas. Work done for both. So let us find out W, which is equal to del U, is equal to N CV into delta T. Since T values are given, so you can easily find out the work done in monoatomic gas. In place of CV, we can write 3 by 2R. Because we know for monoatomic gas, if nothing is given, sometimes the data of CV is given, which is more or less equal to 3 by 2R, may be different, slightly different, you take that data. But if no data is given, then for monoatomic, you take 3 by 2R, for diatomic 5 by 2R. Yes, that is the way, the convention. Although you know for diatomics, anything can happen. It can be 3 by 2, it can be 5 by 2, it can be 7 by 2. That concept you never forget. But usually if nothing is given, 5 by 2 for diatomics. CV, I'm talking of CV. CP will be R more. Then N is 1 mole into 3 by 2 into 8.3 into, this is final temperature is 300 and initial temperature is 600. So it will be a negative work, because expansion work is always negative according to the acquisitive or chemical convention. So what is the value?
Sir, minus 3735
joules. And obviously for this is A, bit 1. And obviously del U is same. They're asking for del U. And Q is equal to 0. Goes without saying. This we have already done. And del H is, you can find out N Cp delta T. You can find out N is 1. Cp is 5 by 2R. Delta T is same, 300 minus 600. You can find out del H. It carries little meaning. It is not carried out at constant pressure. So finding out enthalpy change is just a ornamental thing that is being asked. You can find out that. I'm just leaving to you. It will be minus something. It will be numerically more than del U. Doesn't matter, since it is 5 by 2 here. Similarly,
Sir, it is forming 6225 joules.
plus or minus?
Sir, minus
6000?
Yes, sir, mine.
225.
Girls, are you existing?
Yes, sir.
Yes, sir.
Good. And for diatomics, let us go only for work done. The only difference will be here, N CV in place of CV, we will write 5/2. What we have written for the enthalpy change for monoatomic will be the internal energy change for diatomic 5/2 R delta T, and the value will be 6225 joules, right?
Yes, sir.
And,
Yes, sir.
and here del H will be 7/2. Don't do that. Forget about. More and more interesting problems are coming on the way, so nothing to worry about it. Now see, this is another interesting example which was set in an IIT examination maybe few years before, maybe in IIT main or maybe advanced. I think it is main. Maybe it is from physics, maybe it is from chemistry. I don't, because the problems are similar. But you definitely find in chemistry the sign conventions of W and work done, formula for work done, they are opposite to that of physics. Now everything else is same. Now see, we will not leave anything, we will be doing everything. Now see, 1 mole of a diatomic gas undergoes cyclic ABC process ABC as shown in the figure. First A to B, then B to C, then back to A. The temperature, the process BC is adiabat. Since temperature is changing, it is adiabat. The temperatures of ABC is 800, A is 400, B is 800, E is 600. Find del E or del U, del H, W, Q in each step and the whole cyclic process. Also choose the correct statement. So it is better to keep in terms of R to answer this multiple choice question with a single correct answer. And then, as I have converted this problem into a full blown out numerical to find del U, del H, W, Q in each step, and also ensure that for the cyclic process, you know, that the numerical value of work done is equal to the numerical value of the heat change, and that is Q is equal to minus W holds good for the cyclic process. And since del E becomes equal to 0, that also will add up all the heat, all the W, and you will find the two values are same except their signs are opposite. Now let us take up case by case AB. AB, what is the work done?
0.
And what is the heat? Is nothing but del E. Yes or no?
Yes, sir.
That is equal to NCV delta T. Since number of moles here given is 1 mole, so and CV is 5/2 R because it is a diatomic gas, and delta T is 800 minus 400, final minus initial. So the work has to be, the heat has to be absorbed, then only temperature will rise. Amonton's law. Heat has to be absorbed. So Q has to be positive. So let it be in terms of R. Let it be in terms of R.
Sir, 1000 NR. So 1000 R.
Plus 1000 R. Now let us go for BC, which is an adiabat. How to find, because del E is equal to W. Here Q is equal to 0, as you know. So that is equal to again N CV delta T, and 1 CV is again 5/2 here. This is diatomic. You have to take, no data is given, so you have to take 5/2 R. And del T is something different here. Final is 600. This is expansion. The work done has to be negative 800. So how much R you find?
So minus 500 R.
Minus this
500 R.
5. Okay, then Q is equal to 0. We shall be adding. Then coming to the isobaric process, AC is isobaric, this is adiabatic. This is isobaric. There is a decrease in temperature from 600 to 400 due to decrease in volume, pressure remaining constant. So here we find W is equal to minus P, the constant pressure, into delta V, that is equal to minus NR delta T. So the temperature and volume, they are directly related, so pressure remaining constant. So we can write P del V as NR delta T. So the work done will be minus 1. So this will be definitely positive because, you know, temperature is decreasing. R, this is 400 minus 600. How much?
200 R.
200.
Because since the temperature is decreasing, the work done, this is a compression. This is a compression. Volume is decreasing. Compression is a positive work, and obviously work done will be you know, what will be the work done? Since Q is equal to, so this del, what is work done? What is the Q? QP, this is QP is equal to NCP dt. Yes or no? Since
Yes, sir.
it is the heat which is being added, you know, the heat is evolved. I think it is evolved. Yes. Why I think? Since work is done, uh, um, work is positive, work is, the compression work is done. So the heat is absorbed by the system. It is evolved by the surrounding, but it is absorbed by the system. So, no, is evolved. C to A, C to A is a compression. Compression is a positive work, but the heat, I will tell you. First you find out, then we'll discuss. 1 into Cp is 7 by 2 into 400 minus 600. How much? How much?
Sir, minus 700. 700.
In terms of R, it is minus
700 R.
So before we enter into, so since del U is equal to Q plus W, so here Q is minus 700 R and 200 R is the work done. So there is a net decrease in internal energy as the heat is evolved. Because it is cooling down, temperature is falling down from 600 to 400, the heat is dissipated out. So there is a decrease in internal energy by an amount equal to uh, 500 R. So forget about del U. We are not interested in del U. We are interested to see that in a cyclic process, W, in a cyclic process, net work done is equal to net heat transferred. So what is the total work done? Let us write down. We don't have space. Let me use a red pen. So total work done in AB, AB, it is 0. And in BC, it is how many R?
Minus 500.
0 minus 500 R. And in CA, it is how much R?
200 R.
200
plus 200 R. The sum total is minus 300 R. We will find total Q must be equal to plus 300 R. So here the AB, in AB the heat is 1000 R plus, and in BC it is 0, and in AC
It is minus 700.
in actually it should be CA. It is CA. In CA it is minus 700. So what is the net result? What is
300
the net
minus
result?
300.
300
So
R.
300
Are you
plus,
then
sir, plus.
why are you saying minus plus 300 R? So we proved that the total work done in a cyclic process is numerically same as the heat, here heat has been absorbed and work has been done. Net heat has been absorbed during the cyclic process, and that is the principle of the internal combustion engine. And net heat is absorbed, a part of heat is thrown to the sink, more heat is taken from the source, part of it is thrown to the sink. We're doing that in second law, and the remaining part is used for performing work. The motor runs. So Q is equal to minus W total that we have proved. And out of the 4 choices you find here, what is the correct choice? The change in internal energy in AB. How much AB is 1000? Internal energy is same as Q, is 1000 R, but it is writing minus 350 R is wrong. Change in internal energy in the BC
Yes,
BC
yes, sir.
is the
Yes, sir,
adiabatic
correct, sir.
process, is minus.
This is
This
correct.
is correct. The change in internal energy in the whole cyclic process is 0.
Yes, sir.
Cyclic process rate, this
Sir,
is incorrect. It should be 0. The change in internal energy in process CA is we have found out in CA the internal energy is minus
Minus
500 R.
500
Yes
R.
or no?
Yes, yes, sir.
But it is
yes, sir.
giving plus 700 R. It is also wrong. So the correct answer is B. And as well, I have converted this into a full-fledged this thing. So you found del U, and similarly you can find del H also, and CP delta T, W and Q in each process. And cyclic process also we have found out the total heat absorbed and total amount of work done, expansion work done. Therefore, W is negative and heat is positive because heat is absorbed. How are you feeling, guys?
Good, sir.
Only good? Only good?
No,
Brilliant.
sir. Excellent, sir.
Okay, no, I want a self-motivation so that I am commanding that from you so that I will work a little more passionately. I am usually passionate, as you have seen. In whichever class I am passionate. But this time, the only deviation you are finding that I am delivering in English. Because you guys, whether you are in Odisha, or from Odia medium, vernacular medium, you have to converse yourself in English. So therefore, I have made this formal English, but class is not becoming formal. I am also raising humor from time to time to make you appear as if you are in the same class. I have been usual class I used to take in bilingual presentation. Of course, most of my viewers are also from Odisha. Some people say, why not you deliver in bilingual also in your videos? But I have made it a point. Doesn't matter whether somebody is subscribing to my channel or not. I'm not very desperate or very Yes, the correct word is desperate for that. Yes, if somebody subscribes to my channel, it is a motivation, no doubt. But I must speak in English because you guys, whether you are in Odisha or any other state in or India, in northern India, guys are very allergic to English listening, English speaking, Hindi speaking belt. They shy away from English. They always converse in their teachers. 90% of the time they speak in Hindi, and some words, scientific words, they tell in English. Or else the explanation part is in Hindi. But in South India, they are fond of English. They use more English than they use Tamil or Telugu or whatever. In Odisha, let's talk in English. What is the harm? More you listen, the more confident you become. Now let's to this one. Again, you are back to isothermal. 1 mole of an ideal gas undergoes isothermal reversible expansion from an initial volume V1 to final volume 10 V1. So since it is a ratio, no need to know the actual volume, and does 10 kilojoules of work. The initial pressure is 10 to the power 7 Pascal. Calculate the initial volume. So, oh my God. So from the work, you can find out the temperature. So W is equal to minus nRT. This is nothing to do with CPCB. This is isothermal reversible. nRT log 2.303 you have to bring in, log 10, the final is 10 V1 by V1. So it becomes, and the work done is given 10 kilojoules. That means 10,000. 1, R is 8.3. Temperature you do not know, but log 10 is equal to 1. So you can find out what is the temperature isothermal constant temperature condition. Can you find out for me? This now how this will be negative? So there will be this, because work done is expansion, this has to be negative, my dear. Yes or no?
Yes, sir. Yes, sir.
Yes,
So
sir.
since it is
Yes.
an expansion work, we have to put a negative sign. Once we use that data, which is not given negative, but we have to put a negative sign, since here in chemical convention, the expansion work is negative. So what is the temperature, initial temperature? I mean the
So
constant temperature. Yes,
five
So 523 Kelvin.
523.15.
520
523.15
Kelvin. This is all in Kelvin,
Kelvin.
right? Then you can, since the pressure is given, so you can find out PV is equal to nRT. So V is equal to nRT by P. So N is 1, R is 8.3, T is found out to be 523.15, by pressure is 10 to the power 7. All are in SI unit. So volume will be found in meter cube. How much meter cube? Let me check the answer. Not given the answer here. I have my answer with me. I will check here. Yes, what is the volume?
Sir, 4.342 into 10 to the power minus 4 meter cube.
Precisely. 4.3,
42.
okay, to
145.
10 to the power
Minus 4.
minus 4. So you can also convert it to liter if you are asked liter. Uh, uh, liter. What is the relationship between liter and meter cube? 1 meter
1
cube
meter
is
cube is
Okay, 1000
1,000
liter.
liters.
precisely. If you multiply by 1000, it will be remaining 10 to the minus 1. So 0.434
0.434 liter.
2, or it's to make it 2 here. So liter, you can convert it to milliliter, 434.2 ml, right?
Yes, sir.
Yes, sir.
Now look to another one which is interesting, adiabatic. Both expands irreversibly and adiabatically, not both. Both will be the last problem. We'll be comparing between the temperature drop in this and temperature drop in that. This is a very straightforward question, and maybe guys, who are watching in the YouTube, please don't feel monotonous. If you are really with a pen and paper, usually guys, they love to watch any video of 10-20 minutes duration. Otherwise, just 2 minutes, leave it. Viewership will be more, but the total time viewed will be the average time will be 1 minute, 2 minutes. That happens with every video, unless some guys, they mean business. I'm not talking about them. For them, there is a little more average. For others, it will be a few seconds. Oh. 2 moles of an ideal gas irreversibly. So the temperature drop is given. Then there will be no problem. So whether it is reversible or irreversible, work done is del U is equal to N Cv into delta T. This is applicable for both because the temperature is given, irreversible. So it will be 2 moles. Cv is equal to, for it is a monoatomic, 3/2 into 8.3 joules into delta T is 275 minus 325. So what is the work done? It has to be negative because in expansion work is negative here. So what is the work done?
Sir,
So 1245 minus 1245.
So I have just rejected the pressure data. We can get the same value against 1 atmosphere. If you take this as the constant pressure, you need the change in volume. So you have to find out again PV is equal to nRT 2 times to find the initial volume, final volume. No need. This data is superfluous for us. Since the temperature data is given, we can straightway jump to NCV delta T and we can get the work done, which is same as change in internal energy. How much?
sir, minus 1255. Sir, I have taken the CV data given in a question.
A question is HCB data. Oh, I'm so sorry. I'm so sorry. You can't take 3/2R. Once the data is given, you have to take this one, 12.55 joules per Kelvin per mole. This is molar heat capacities. That is why per mole. Therefore, you are multiplying by N. the number of moles. So Ketya, how much you are getting?
Sir, that much, 1255.
Yes, sir. 1255.
So there is a decrease in internal energy when there is expansion. Calculate W and initial volume. Then you can find out initial volume. PV is equal to nRT can be applicable to find out pressure is known. Oh, that is why pressure is given. The initial pressure is given. Initial temperature is given. So initial volume is equal to nRT 2 into 8.3. Temperature is initial temperature is 325. By pressure, you know, it is 1.01. 3 into 10 to the 6 initial volumes. So you can find out that will be coming in meter cube. Forget about it. Truly forget about it and look to this problem. 1 mole of an ideal gas initially present in an insulated. You might be wondering, if it is not an ideal gas, it is a Van der Waals gas. Then situation is a bit complicated. I'll tell you how A and B Van der Waals constants will be taken into consideration to find all these work done. So usually you don't get any question on Van der Waals gas using Van der Waals constant A and B. It is very complicated. I mean, the calculation is bit involved. I will tell you that also. But 99.999% of the problems that you face are ideal gases. I mean, they behave ideally. 1 mole of an ideal gas initially present in an insulated piston fitted cylinder 400 K and 10 atmosphere is allowed to expand against constant 1 atmospheric pressure. That means irreversible till the mechanical equilibrium is established. CV is given. Undoubtedly, it is diatomic gas, no doubt about it. Determine the final temperature of the gas and the work done by the system. Calculate the temperature attained if the expansion done reversibly. What will be the work done in this case? It's a very interesting one, and that probably will be the last sum. And we will declare the end of the first law, and we'll go for the second law. Much more interesting than the first law is the introduction of the phenomenon or the thermodynamic property called entropy, which is also a state variable. Let us equalize n Cv delta T as minus P external delta V. So you have to somehow, this Cv is 5 by 2R, n is 1, Cv is 5 by 2R. Say this is the initial temperature is given, final temperature is not given. Say this T final minus 400. This is delta T. This is, and the other one which is exclusively for irreversible is external pressure is given 10 atmosphere. So we shall be using R as atmosphere and liter volume. So doesn't matter. And here is V final minus V initial. Now since PV is equal to nRT can be used in the initial state, we can find out the initial volume as nRT by P. Since the initial pressure was 10 atmosphere, the number of moles is 1, R is 0.082, temperature is 400 by 10. So you can find out in liter what is the initial volume. but we do not know the final volume. Because we do not know the final volume. Had we known the final volume, then we would have got the temperature, no doubt about it. So what is the initial volume?
So 3.304 liter.
Let us forget about 0.4, 3.3. So initial volume was 3. Here we can write C. How can we get this? Is again 0.082. TF minus 400 is equal to minus 10 into V. How can we convert in the as a function of temperature, final temperature? Tell me, the final pressure is given. So to remove V final, what can we write?
Sir, from PV equal to nRT, you can write
R is
nRT upon P.
nRT final, nRT by P. P is equal to how many atmosphere? 1 atmosphere. Yes or no?
Yes, sir.
Since PV is equal to nRT is applicable for both initial and final state, the final pressure is 1 atmosphere, and the final temperature we have made it as TF. So nRT by P is equal to V. So in place of V final, write N 1 mole, R 0.082, T final by 1, and the initial volume we already know, that is 3 how much? 3 liters. So here the only variable is TF. So can you now find TF for me? I'm feeling very happy to take classes because you guys, at least 2 of the boys, are very fast in calculation. That motivates me to go till end. Otherwise, I would have said, do this way, do that way. You will get the answer that usually we do. That will not give you a good conceptual clarity on each aspect of a subject. There are so many other problems you can do of your own. So what is the TF? I give you 1 minute time. Maybe it is going to be now 2.5 hours. I think there is nothing. This is the last. This is the climax scene. We'll be doing that. I will not leave you until the last problem is solved. This is almost on the verge of solving this. I have to take this down because it will consume more space. Are you calculating or I will?
Yes, sir.
Sir, 112 Kelvin.
Is it okay, Mr. Rudra? Or else I will look to my answer. I have my answers. No.
Sir, I am getting 1007.
No. No. Both of you are incorrect. Are you kidding me? It was initially 400 and it will be cooled down because of the expansion. It will be cooled down. It will be less than 400. How can you say it's 1000? Then some calculations we have done wrong. You have to look to it again. Oh, the great mistake, guys, we have done. Who can tell me? There is a serious mistake that we have encountered. Serious.
Sir, maybe we have put a data in liter.
No. Yes, Omkar?
So,
Anyone what
external pressure
should be?
is 1.
Precisely. Omkar now becomes Sikandar ka Mukaddar ka Sikandar. Yes. Because in irreversible expansion, the external pressure is the final, the lower final pressure 1. It is expanding under the final pressure as constant pressure against a constant pressure of 1 atmosphere. So by mistake, we have written 10 here. This is so very weird. Got it? Girls, you got it?
Yes, sir. Yes, sir.
Girls?
Yes, sir.
Yes, sir.
So instead of putting 1, we took the initial pressure. No. In expansion, the final pressure is the constant external pressure under which the expansion has happened. So you make a fresh calculation taking as 1 and tell me what is your answer now.
So 297.2 Kelvin.
Precisely 297.2. It was 400, now reduced to 297.2 in irreversible expansion. Let's see what happens in reversible. Okay, and accordingly you can find out now the work done is equal to n Cv is equal to 5 by 2r. If you want to in terms of joule, then y2 0.082, let us 8.3 into the final temperature is 297.2 minus initial temperature is 400. So the expansion work has to be negative, and this n is equal to 1. This is 1 mole. So what is the value of work done here? What is the value of work done here?
So minus 2132.839.
So this is the work done and the same as delta E. There has been a decrease in internal energy. Del E is negative, same value. W is also negative, same value. Now let us go for reversible. For reversible, the adiabatic gas laws has to be used to find the final temperature. That is, since temperature and pressure data are given, volume data is not given. Final volume we have not found out. We can now, because the final volumes will not be same under adiabatic condition. The temperatures are different, their volumes are also different. So it's not showing that the same volume has been attained. It's saying if you carry out reversibly, then what is the work done? So it is better to use a relationship between temperature and pressure. T1 by T2 to the power Cp is equal to P1 by P2 to the power R. Remember this whenever you want to correlate between temperature and pressure. So the two temperature, out of that the final temperature you have to find out. T1 is known, P1, P2 are known. Of course, you could have found out the volume there, final volume, then T1 V1 gamma minus 1 is equal to T2 V2 by gamma minus 1. You could have done because you know the final pressure 1 atmosphere, and of course the final temperature is in on a no, you have to use this. The final temperature was in a irreversible expansion, not reversible expansion. Uh, Since you are bringing to the same pressure, there the adiabat and isothermal, sorry, the reversible and irreversible. Irreversible is this much and this much. So we just look at home by using the irreversible temperature of 297.2, whatever volume you find, use the same volume here in T1 V1 gamma minus 1 is equal to, because as I was thinking that this is the adiabat, reversible adiabat, and this is the irreversible expansion, which is this area. So if you are coming to the same volume, then maybe the temperatures are different, but the volume would be same. So you can use the irreversible temperature to get the final volume and use that volume to find out the new temperature under adiabatic, under reversible expansion. This one. You have done this one and got the temperature 290 something, and find the volume PV is equal to nRT. Take that volume to find T1 using the adiabatic gas laws to find the final temperature. Do at home, but now use this to find the final temperature. T1 is how much? 400. 400 by T2 we are going to find out, to the power Cp. Cp is equal to what? What?
7 by 12.
7 by 2
2
R is equal to P1 was 10 and now it is 1 to the power R. So RR get cancelled. Yes. So it is simply 400 by T final to the power 7 by 2. RR get cancelled. So it will be 10. So if you take the log and do the needful, can you find out what is TF?
Sir, it is coming around 207.
Let me see my answer. Oh,
Yes, sir. 207.
yes, it is 207 point something. How much?
Sir, 25.
0.25 Kelvin. Now see, that was 290 something, and in reversible expansion, both adiabatic, there will be a cooling effect. The area is more, this area is less, so the temperature drop is more, and the final temperature is numerically less, 207. Now, once you got the same principle, W is equal to del U is equal to my N Cv, that is 5 by 2 R. Is it given the value? No, it's simply saying pi by 2 R into delta T, that is 207.25 minus 400. So find out here the work done will be more. Work done, expansion work done will be more because the area whole by under the whole adiabat. How much?
The minus on 3999.56.
Much greater. It was some 2000 some odd in the irreversible process, where here it is nearly 4000 joules, much greater. Now your home task will be to find out the final volume using that old temperature, and then using T1 V1. Let us do it now. We will be doing this at home. This will be a home task for you. And now you find alternative method. So to find the final volume is nRT by P. R, since pressure is 10, 0.082 into temperature is 297 or something, according to Irreversible 97.2, by pressure is 10 atmosphere. So find out the final volume.
Sir, 2.437 liter.
And use the adiabatic gas law. Now, T1 V1 gamma minus 1 is equal to T2 V2 gamma minus 1. That is, temperature initial is 400 into volume was 3.3 to the power gamma. Gamma is gamma is for it is 1.4. I think it is a diatomic gas. It is diatomic gas. 5 by 2 R means it is a diatomic
Yes, sir.
gas.
Yes. That.
So it is 1.4. That means gamma minus 1 is 0.4. So to the power 0.4 is equal to T2. We have to find out. V2 is just now you found out how much? How much? How much?
So
Sir,
2.437.
2.437 into to the power same 0.4. So here you find out what is T2. You take if required, you take the log and then anti-log. T2 by 400. T2 by 400 is 3.3 by 2.437 to the power 0.4. So log of this will be equal to 0.4 into this. So I'll give you 1 minute time, find out T2.
Sir, 451.56.
Yes, sir. 451.5.
Is it coming 207? No.
No, sir.
So this cannot be taken because that volume is based on irreversible expansion. It is not telling about the final volume. It is telling about pressure. At 1 atmospheric pressure, it can, it is here, the bound. But this work done is about the temperature difference is large. The work done is about 4,000. How much? Work done is about 4,000, whereas this work done is less. So so the two volumes are not same. The final volumes are not same. In irreversible expansion, the final volume is 2. How much? 2. How much? 2.437.
437.
So this you can just cancel out. This is irreversible. The final volume is T2 is coming this. So there is no need to, because it is going irreversible. So the adiabatic gas laws are not applicable here. Simply is not applicable here. But we can prove that PV is equal to nRT to find the final volume in a reversible process, nRT by P. So N is 1, R is 0.082, T is 207.25 by pressure is 1. Here you find still lower volume because temperature drop means volume is also less than what is irreversible.
Sir, approximately 17.
What
Yes,
17?
sir.
It was 2.7, it was 17. Are you kidding me?
Yes, sir. It's coming 17.
Yes, sir.
17 liter.
16.99. Yes, sir.
That means it was initially 3.3 expansion. Yeah, but how come that here you get 2.7? It was originally 3.3. I think you your calculation was wrong, because whether it is irreversible or reversible, there is expansion. The final volume will be greater than the initial volume. You have got 2.7 something, which is less than the initial volume. So you have to work again at home, right?
Yes, sir.
Hey, how could you get 2.7? I was really wondering. Once again, you see, I'm not going to leave. This problem is your home task. We'll do it tomorrow, or maybe tomorrow. Are you free, Priyani?
Yes, sir. Yes, sir. Tomorrow, sir.
Priyani is not here, but we are not very much keen. Priyani is not able to give her 100%. So she can watch. She is very generous in that. She can watch the video later. So irreversible is the final volume is nRT 0.082. T is 297 point something by pressure is 1.
Sir, we had taken pressure before as 10. That's why it was coming 2.437.
No, it is 1.
Yes, sir, but before we had taken 10.
Oh, you should have pointed out. The same mistake we did
Yes, sir.
for finding the work done through constant external pressure of 1. We made it 10. Now you are going to find the final volume. We are taking 10 instead of 1. Find out once again. You must point out my mistake. So find out that. I'm not going to leave you unless this is settled out graphically as well as mathematically. Saminani, it is 9:20. This is going to be over once for all. Usually in chemistry classes, you don't deal with so much of thermodynamics, so intense thermodynamics. It is only done in physics classes.
Sir, 24.37 liters.
Use that again. T1, V1. Use 24.37. And you got in reversible, it is 16.99 or approximately 17. Okay. And then use that T1 V1 gamma minus 1 once again to find the final temperature. Ultimately to discard that no. So T1 is 400 into V1 is 3.3 to the power 0.4 gamma minus 1 is equal to T final into 24.37 final volume into 0.4. So from here, you find what is TF. Let it be 2 minutes more. Let it be now. It's going to be 9:30. Started from 6:30 to 9:30. We are almost on the threshold of completing 3 hours. Never mind that. Since you
Sir,
guys
179.77.
Yes, sir, 179.7.
And what was our answer by using the other relationship? 200?
Sir, 7.525.
So still they are not same. So this has to be rejected. So this, see, final volumes are not same. So it is better to correlate between pressure and temperature to get the final temperature rather than to use the volume from the temperature in a irreversible expansion and using that volume using V1 T1 into T1 V1 gamma minus 1 constant. That is not the case. We have proved that this is wrong. So this comes to an end of our today's class. Now let me show you how you solve this? I'm giving you the graph. 1 mole of an ideal gas, monoatomic gas, expanded adiabatically and irreversibly like this from A to B. You have to do it. A, pressure is 1 atm and 22.4 liter. Since it is 1 mole, the temperature has to be 273. The temperature has to be STP, that is 273. It is understood PV is equal to nRT. 1 mole, 22.4, 1 atmosphere. So it is definitely 0 degree Celsius. Then, and it is doubled. Therefore, the temperature has to be doubled. No.
No,
Since
sir,
it is,
pressure
no,
decreased.
I'm so sorry because it is adiabatic. Adiabatic. The temperature will not remain the same. It will be less than 273. Find out that. Then B, to C, it is a reversible isothermal compression whose line is going below. Because for the same amount of volume, the temperature will be more in, we are going in this direction, isothermal temperature is remaining constant. But if you are going in this direction, then you will find there is a greater temperature, so greater pressure. Therefore, for isothermal compression, graph will remain below the adiabatic graph. This is reversible adiabatic. Go the expansion and compression go in the same line if it is done quasi-statically or reversibly. Then after coming to C, it is heated isochorically straight to join A. This is isochore, this is isotherm, this is compression. Therefore, the graph is running below the adiabat. This is adiabat. See, this is adiabatic expansion. This is isothermal compression. And then this will be simply, heating to get the same 0 Kelvin because this temperature will be dropped. So from B to C, the temperature will remain constant because this is an isotherm. Then C, there will be again heating coming back to 273 K. So depict the process on a PV diagram, which you have already done. Find Q, del W, delta E, and del H for overall operation each step, and then you add up. It's a cyclic process. You'll find W is equal to minus Q or Q is equal to minus W. That is the end of today's program. I thank you very much to remain with me for continuous 3 hours course with a 2 to 3 minutes break in between. And those who are still watching from a distance, hats off to you. You are not with me almost directly as these guys are. Still, you are continuing to study with me. Hats up to you. God bless you. See you tomorrow. Shall we sit tomorrow?
Yes,
Sir,
sir. Yes,
tomorrow
sir.
I can't.
Yes, Samida? Yes?
Sir, tomorrow
Yes.
I can't.
Tomorrow she can't. So we'll have to think. Let it be day after tomorrow. No worries. Since we have taken 3 hours of class, we can miss out to tomorrow's class and we can sit day after tomorrow. Day after tomorrow, you are free?
Yes, sir.
Okay? Guys, the guys are
Yes, sir.
very passionate, but the girl is having so much of activities that she has to give justice to all activities. Bye bye. See you day after tomorrow. Today is which day? Today is Wednesday, and we'll be meeting on Friday at the same time, 6:30 in the evening. Bye. And if you have not subscribed to my channel, those who are watching from a distance, I'm telling at the end, most of you might have closed. Please subscribe to my channel. Bye bye.
Good day, sir. Bye, sir.
Thank you and a very good night, peaceful night and sound sleep.
Thank you, sir.